chapter 5 about Heaps and algebraic graph theory. So from the previous lecture, what we have done in the first part of chapter 5, we have defined the matching polynomial of a graph, and we studied the zero of the matching polynomial, and we studied also the chromatic polynomial of a graph, the number of ways to color the graph with lambda color. It's a polynomial, and we have seen a famous, very classical theorem that the value for -1 of this polynomial is up to the sign, the number of acyclic orientation of a graph. Yes? Question? Yes?
This mg was a polynomial in X squared.
The matching polynomial?
Polynomial was a polynomial in X squared, wasn't it?
Or we replace x squared by t by only yes.
So the statement is that polynomial has real roots. Or
Real roots.
After you replace by t, will it make a difference? See before.
Yes. Yeah. It's just I put t for one edge. T equal x to the square. It was t. Yes. Yes. Mm-hmm. And then we have seen multi-chromatic polynomial with k color on each vertex. Several vertex can be colored with several colors. And then we have introduced the chromatic power series of a graph. It's related to general heap with multi-layer color heap. So this was the last time. And then last time I introduced a kind of research problem with Green-Zaslavsky, giving an interpretation of the number of acyclic orientation with only one thing. It's going to be related to the linear term of the chromatic polynomial. In fact, I have forgotten. I know Bodolas, and he told me about a lot of pyramid and chromatic polynomial, but I have forgotten his paper that in fact he is working with what he calls set function d'ensemble. It's an algebra of function where the square of a variable is 0. So it's related to the Grassmann, what we have seen, the Grassmann algebra. But so he gives interpretation not only of the linear term, but all the term of the polynomial. He gave some interpretation as number of components of the acyclic orientation. In a certain way, number of components. So, but everything is done with set function, and then this is related to heaps of pieces. So maybe it's exercise or research exercise, retranslate everything, this work, in terms of heap directly, and maybe do this not only for multilinear heaps, which give you coloring, but for multicoloring. So do this for general heaps, for the chromatic power series, to interpret the coefficient. Maybe it's interesting to do that in general for any heap. There is some pyramid, some component inside. So function d'ensemble, set function, is more or less also related to working with exponential generating function. So in this story, you need the heaps with exponential generating function. Put a labeling on the heaps and factorial times. So this was last time. I don't want to go further longer on this. Today, we introduce another algebraic relation with graph, the zeta function of a graph. There are several zeta functions. So the idea is to extend the classical Riemann zeta function to extend it to any graph. And this is usually called the Ihara zeta function or Ihara-Zellberg zeta function. For any graph, we are going to define a zeta function which reduces to the classical Riemann zeta function in the case of this graph, in the case of trivial heaps. Trivial in terms that there is no relation on the concurrence dependency relation. There is no relation at all except that A is in relation in A, which means that all the variable commute. You are in the free abelian monoid. Here's a heap, you see it's the blue ball and the red ball. So in fact, it's indexed by the prime number. And of course, any number is factorized in a product of prime numbers. So the zeta function is just the sum of the weight of all this, where you weight each column by the prime number power minus s. So if you take the sum of all this will be the sum of all this in terms of Heaps. Maybe it's trivial to translate this in terms of Heaps, but because we want to extend this to graph, so we have to make Heaps to replace these balls are just loops, in fact. They are loops, and we are going to replace them by cycle or circuit or something prime cycle. So we have to replace this by something prime. And so the inverse, we have seen in the chapter on Möbius function and inversion, the inverse of the Riemann zeta function is this given by the Möbius function. So it's just translate the generating function for Heaps is inverse of the generating function for trivial Heaps, and trivial Heaps is just when there is at most one ball in each column. So at most in the prime decomposition, the index alpha I are 0 or 1. So this is just the generating function of Heaps as the inverse of this generating function of trivial Heaps. Now, because of this very special case that each fiber of the heap are totally independent, there is no relation between putting heaps of ball here, putting heaps of ball here. So you get the so-called Euler identity, that the zeta function is a product of this. This is a generating function for one single fiber, all the fiber on one column. The weight is prime number minus s, so it's 1 over this, and product over all prime number. Maybe it seems stupid to this classical arithmetic number theory to put them in terms of heaps, graph, and everything. It is trivial, but because we are going to extend this to heaps of cycle on a graph, so it's good to see what is the extension. So the idea is the following. You take the Euler formula, expressing the Riemann zeta function as a product over all prime number of 1 over minus something prime, and I would like to extend it to graph by having an analog formula. You have to replace prime number by something which is written bracket equals C. It's going to be some prime over the graph. The prime we are going to define them. There will be different zeta function according to what you define a prime on the graph. So here in the Hilbert zeta function, the prime is going to be related to circuit, prime circuit up to an equivalence relation. So let's recall our definition of circuit, cycle, elementary circuit, etc. Maybe it's not the standard definition used by people in graph theory. You have the question? Say something which bothers you. I did not yet define what it means prime. Let's wait. This is the idea, is to define some prime. And I'm going to give a precise definition of what I mean by this, the class of C, and what I mean by C over prime. So let's do the definition. So first, a circuit, I remind you, a circuit is a path. For me, it's a path, omega, going from U to U. Starting point is U, ending point is U. This is a circuit. Sometimes in graph theory, they call it a cycle, but for me, it will be a circuit. It's a closed path. The origin and ending point are the same, and I can make the product of two paths by putting them concatenation of the path. You go from U to S, and then you go from S to T. So you can concatenate if the ending point of the first path is the same as the starting point of the second one.
So this could have self-intersection.
It's any path in general. So if I have a circuit, I can take the power of a circuit. If you have a circuit C, then omega going from U to U, so I can take the power omega power P. Means I am following P times the same circuit omega. And a prime circuit definition, it will be prime if you can write the circuit as omega the power of another circuit, then P equal 1. So this is prime circuit.
Goes round only once.
You go around your thing only once. You can intersect many times yourself, but you maybe you can pass several times at the U, but once you have done a circuit, then you can make the square of the circuit, the cube of the circuit, you see, and a prime circuit means you cannot find an omega such that C equal omega power P. This is prime circuit. No, it's not elementary circuit. It can cross many times itself. It can go several times at the origin U. But when you go back at the origin U, the next portion is not going to be the same as the first portion you have done. So this is a formal definition. Prime circuit. It's a big class. Huh? And then I will take the equivalence class of prime circuit or of circuit. It's a circuit. A circuit is a word in terms of edges. It can be a word in terms of vertices. But if you look the edges between two vertices, S0 to S1, S1 to S2, S2 to S3, so you have a word in edges. Each edges, the ending point of an edge is the same as the starting point of the next edge. So as a word of edges, you take the conjugate class. Conjugate of a word is UV and VU. You cut the word and then you transpose the two parts of the word. So conjugation of words give you conjugation of circuit. And I take the equivalence class of the circuit. Intuitively, it means you forget the starting point. So let's compare with what we have done before. Here is three things. Here is a circuit, the image of a circuit. I go from U to V, and I cross myself several times. This is an elementary circuit where all the vertices are distinct. And this is what we call a cycle. As a cycle of a permutation, we have many heaps of cycles. This is an elementary circuit up to a circular permutation of the vertices. So this is a class of elementary circuit. So here for the Riemann zeta, for the here Zelberg zeta function, we are going to do this circuit. We are going to take prime circuit and up to a circular permutation of the word which is formed by the edges of the circuit. Which means you can start at any other point, take this point here, for example, and start from this point, and you have another circuit. So the class is such circuit up to a circular permutation, means you forget what was the origin and ending point of the circuit. And so the definition of this Ihara-Zelberg zeta function is a product of all this, 1 over 1 minus t, power the length. This is the length of the circuit, and the product is over all equivalence class of prime circuit. There is something I will define. So you know what is a circuit, you know what is a prime circuit, you know what is an equivalence class of a prime circuit, and now I have something more, which circuit with no backtracking. So at the beginning, Ihara, he defined this for special class of graph, regular, etc. And some people, after, it was extended to any graph. But at the beginning, it was much more restricted. So what means no backtracking? So if you have a circuit, not an equivalence class, but take a circuit starting at U and ending at V equal U. So here is a circuit, you see. I have some part in brown, I have some part in green, and here I have some part in red. So this is a backtracking. Backtracking in the path means you are at vertex I, you go to vertex J, and immediately after you go back to vector I. So we have seen tree-like paths. Tree-like paths are always doing backtracking. Else they go further, extending the self-evolving path, eta, which was in blue in all this class. Or else you go back on the step and you make a backtracking. So for different reasons, people want to restrict the product to prime circuit with no backtracking. But what means a prime circuit equivalence class with no backtracking? It means that if you were taking a representant of the equivalence class, like this one, start in U and end in V. This is called a tail. The tail is when in U you start with these edges, maybe you do many things, and you go back on the same edges in the reverse way. So this is not a backtracking, this is a tail. A backtracking is two consecutive edges. A tail here, these two edges are not consecutive. But if you take the equivalence class, this tail will become a backtracking in the equivalence class. So to say, I just say no backtracking in the equivalence class, it means that if you fix a starting point, there will be no tail and no backtracking in the circuit.
But I don't understand.
Yes.
How will you get the Riemann zeta function if there is no? How do you put in the p, the prime number p?
This replaces the p. It's
No, but in the factor, in the what do you call it, Euler factor, then you have 1 over 1 minus p to the minus s. But here you always have t to the c.
So let's go back to the image, the slides. Yes. The slides. Can we see the slides? It's here, you see. So here, what are each point is a loops. What are the cycle? The circuit are loops. Prime circuit are just loops. So everything is loops.
But where do you get 11? Where do you get 11?
See, variable t is just a number. Each ball is weighted by t. It's no, the t is replaced by the prime number power minus s.
So then maybe here you want weight of c.
The weight of, in this case, the weight is p power minus s, and I replace this by t. It's in the.
So you want to say weight of c rather than t to the power c.
So it's t power the length of c. The length. So in my case here, the length is 1, so it's t. Each prime circuit here, it's just a point. It's reduced to a loop, which is weighted t. And for the Riemann zeta function, I replace t by prime number power minus s.
How do you get terms for each of the prime numbers?
There's only one t and
Yes.
infinitely many primes.
Yes, because zeta function, I should put a weight. Here I just put t, but the general zeta function, you put a weight.
Weight of c.
To simplify, I just put a t, as everybody in all the paper, it was t, but in fact it's weighted zeta function, and you put a weight for each edges. So I want to simplify too much, but so this is a zeta function with a weight, will be this zeta function from number theory.
But in this instance, we only care about the Riemann. In this city.
So here it will be the weight. So each edges will be weighted. So I should put the weight v of the cycle. And then the weight will be t multiplied by another weight. For each edges, there will be a weight, and then you can go back to the number theory Riemann function by putting the weight equal p power minus s prime number. And so no backtracking means if you are working with a representant, a circuit, if you starting point, ending point, which are fixed, then means no tail, no backtracking. Maybe in some paper you will see equivalence class for prime circuit with no tail, no backtracking. But in the equivalence class, no tail. A tail is just backtracking. There is no need to distinguish tail and backtracking. So there is a second definition. There is some formula which are due to Baz. That second definition, it's also can be written as the inverse of the determinant of 1 minus ht. We will define what is a matrix H. And third equality, it can be defined also as this rational fraction multiplied by this beautiful determinant. I will define M, N, A, and D. This is Baz formula. So M will be the number of edges in the graph. N will be the number of vertices. A will be the adjacency matrix of the graph. And then I will define D and H. So the purpose of this class is to prove the equality of these three identities.
Can you repeat what M and N are?
M is the number of edges of the graph. N is the number of vertices. A is the adjacency matrix. So if I don't have this term, see 1 over determinant of this should be the Heaps of cycle. If I cancel this term here. But this term is due to no backtracking. So I have to define D. This is the identity matrix. And then there is also an identity like this with H, a much bigger matrix. So we will see. To prove this 3 identity, I will take T times the logarithmic derivative, T times derivative logarithm of this. We like this, inverse of determinant, inverse of this, inverse of this. All this is a heaps of, so taking this is referred to Jacobi identity with exponential, trace, log. So we are in familiar ground, and I will show you, maybe not completely. I mean that you will see, an evolution is not totally finished. So we'll try to show that they have the same logarithmic derivative. So a few names about all this domain. It's a huge domain. There is many papers. So Bass was giving these 2 identities. There are also some paper to compute, to define this ERA's zeta function in function, to give these 2 identities 2 and 3. And then there is Stark and Terrace have done 2 big paper in advance in mathematics. Even they have written a book on this zeta function and extension to L function, like Artin function in number theory. And then there is these 2 identities. There is some bijective proof by Nordschild, Freitas, Zellberger of the equivalence of 1, 2, 3. But Freitas, Zellberger, they use the notion of decomposition of a word into cyclic words, Lindon words, decomposition. So I try to avoid all these things and just to work with Heaps and the logarithm of Heaps and pyramids. Also, there is a paper Bartoli where he's counting the number of backtracking. He put an extra variable. So if you put the extra variable equals 0, means you don't care about backtracking. And this formula simplify. And then there is many papers. Many other papers, so it's a tremendous number of papers, and it's also many papers in relation with quantum walks. I will not go into all this, but just to show you that it's a huge subject with many topics. And finally, there are some of the more recent papers by 2 French people, Giscard and Rocher, who have done some papers and try to extend not only the zeta function, but all functions from number theory to extend them to graph theory. And once you have the extension, try to understand what happened, and maybe to have to go back to number theory. This is the hope, to have some result as a consequence, going back to number theory, once you have a big detour in the graph theory, Heaps, where you have much more freedom, much more things to say when you are working Heaps of cycle. Just imagine the Heaps of cycle in a graph, and in my graph of the usual Riemann zeta function, the Heaps cycle are only loops. Circuits are only loops of length 1. And so first, taking the logarithmic derivative of this is not difficult. Taking the logarithm, it's just given by this, the definition of the logarithm, the sum of logarithm of this, which is 1 over p, t power p times the length of c, definition of logarithm. So take the derivative, give you this. Derivative of this, the p is going to cancel. So what you get is sum over all equivalent class of prime circuit with no backtracking. The sum over t power p times the length of c, and here the length of c. But it's restricted to equivalence class of prime circuit. But any circuit is the power of a prime circuit in a unique way. So I can rewrite this as a sum over all equivalence class of circuit, t power the length of the circuit, and multiplied by the length of the circuit. And circuit with no backtracking. But if you take a circuit multiplying by the length means you fix a point. The pair of the circuit plus a choice of an integer between 1 and the length, you are fixing a starting point, which means that this is equal to the sum of the whole circuit, t power the length of the circuit. But now, when you go back to circuit, there is no backtracking, but you have to say there is no tail also. When you are fixing the starting point.
You don't have divide by p there. In this formula coming from,
This one.
yeah, from that one to the next one. Replacing p times c by c.
No.
C to the P.
Actually, you should put equivalence class of omega. It would make sense.
No, then until using a p.
Ah, yes, it's the C. Yes, the C is not the same. The C here, yes.
Omega, it replace C by omega.
Yes, I should put omega here. Yeah, yes.
Like then
Yes, omega is C power, so I should put omega.
Omega is C power P.
Mhm.
that's length of c, no, rather than length of omega.
P times C is length of
So I should put length of omega, yes. No, here it's the class. Here I should put the length of omega.
Divided by p.
No, why divided by P?
C in the formula.
Length of C squared is length of C plus length of C, 2 times length of C. So this is really.
See, this is omega. So omega is the length of omega.
In the exponent, right?
The length of omega is P times the length of C.
So that P has gone.
And here it's length of omega. So the P has gone. When I take the derivative, the P disappeared.
There was no P times length of C over here. If it was P times length of C, T to the P times length of C, this would be fine. But maybe there are P circuits which have the same power, P to power.
Yeah, when I take the derivative.
This thing of classes. If you take a 3 thing,
Oh yes, yes.
6
Omega by P.
then there's
No,
6
no.
possible.
So
Yeah, I think that's where it's.
yeah. the P
So I
of
think
P.
1P is because the equivalence class. Yeah, so maybe the intermediate step is not correct.
This time, this step,
Omega by P you have to put like this. Yeah.
this step is not correct.
I think so. Yeah.
Write omega and write
Omega here.
omega by P. Length of omega by P and P power.
Or you can write length of C by P,
Yeah.
but
That's,
still. Yeah.
that's also fine.
Yeah.
Length of C by P.
Why length of c? Length of omega by p. C is the
No, omega is a circle. Let's not confuse things.
Rename omega as C.
But this is correct.
Yes, that is correct, but that is
Yes, okay, I will correct. That's correct. Okay, so we get circuit, same starting point, same ending point, with no tail, no backtracking. So now we are in familiar ground. The circuit is like a pointed cycle pyramid. We have this, so this is t times the logarithmic derivative of the Riemann zeta function for graph. But there is this condition, no tail, no backtracking.
How do you get that last equality when no tail, no back? On the last line.
Because the restriction was, you see here on the definition of the data of the data function, it's the equivalence class of prime circuit with no backtracking. But when you fix the starting point, ending point, you have to say that the circuit has no backtracking, but no tail. Why no tail?
backtrack.
Let's go back to the picture. Where is the data? Where is the?
Tail may be manifested as a backtrack.
So from one equality to the other, you're fixing the
Here, you see, take a trail. A tail. Here, take a circuit starting in U, ending in U. This is called a tail. It's not a backtracking. Here it's a backtracking. It's backtracking 2 consecutive edges. You go and come back. A tail, you go on the edges, you do everything you want, and you come back on the same edges in the reverse direction. This is a tail. Now, to say that circuit has no tail and no backtracking is equivalent to say that the equivalence class of the circuit, there is no backtracking. Because the tail becomes the backtracking. The tail makes sense only if you have an origin. So no tail, no backtracking in the circuit means equivalent, no backtracking in the equivalence class of the circuit. Okay, so I continue. Okay, now maybe no backtracking for omega. That it means no cycle of length 2. This was an exercise, because when there is a backtracking, you can think, okay, a cycle of length 2 is falling down. You remember there was always backtracking. The tree-like path is make a heaps of cycle of length 2, which was a heaps of dimers, which was used in the section about tree-like path. But some people may think that there is a relationship between the two. This was exercise. So I can show you some counterexample that there exists backtracking without cycle of length 2, and there exists cycle of length 2 without backtracking. So there is no way to give a characterization with the usual bijection key. So here is an example of the path. The path is, see in green, 1, 2, 3, 4, 5, 6, 7, 3. So you go back here. So the cycle, and then from 7 you go to 2. So this gives you a heaps of cycle. The heaps is this. First, the cycle gamma in green is falling down. And then there is a cycle of length 2, D, 2 through 2, which is falling down. Eta, the blue path is 1, 2. But in this path, there is no backtracking. It says because the cycle of length 2 is using two different edges which are not consecutive. So there is no backtracking for omega, but there exists a cycle of length 2 in the heap. Now, a second counterexample. There exists a backtracking with no cycle length 2.
But I thought omega should be closed, right? It should start and end at the same point.
When it is closed, it's go back here from 2, go back to 1. It will be closed. You will have a circuit with no backtracking. Well, but you can from 2 I can go here, and then go here. So I will suppose I have a vertex here. So I will make a cycle of length 3. So I will have a heap of 3 things, with including a dimers, and there was no backtracking in the path, and even no tail if I continue. So now second counterexample, if I take this path, you see 1, 2, 3, and then you 1, 2, 3, 4, 5, 6, 7, 8. Again, you are doing making a cycle gamma, and then from 3 you go to 7. So the heap is reduced to this cycle. The blue path is reduced to 1, 2, 3, 7, but there exists a backtracking. The backtracking is 7. It's here. See the red part? I am in 7. I go to 3. I go back to 7. But there is no cycle of length 2. It's because when I do this backtracking, the cycle of length 2 is split in two parts. One part is going in the cycle gamma, and the other part is belong to the self-avoiding log eta. So to characterize path with no backtracking is bijection key is not very useful. So we need a second bijection. We need the bijection psi, which is going to give a characterization of path with no backtracking. And psi is another bijection very interesting because there is a paper on solving the Ising model where Helmut used, the author of the paper, he used really this bijection between path and heaps of something. So the bijection is simple. It's take any path on the graph G, a path on vertices V, and then I define to any path a path of edges, a sequence of edges on the oriented. So sequence of edges for the path you have S0, S1, S1, S2, etc. Sn minus 1, Sn. So this will be a path. A sequence of edges will be a path on what is called, we have seen the line graph the median graph at the very beginning of the course, there was a starfish, remember, to show that any heaps was a heaps of subset. So if you take this median graph, so I define the median graph. This is the path in the vertices are edges. So we define the oriented line graph. So we have a graph, VE, with some edges, non-oriented edges. Then the oriented line graph, the new vertices are the oriented edges. And then you put an edge between this vertex and this vertex if and only if V equals S. So we are working with a line graph. Vertices are edges and adjacency are if two edges are adjacent. Now it's an oriented line graph. So it's much bigger. The vertices are oriented edges. And the new, or I will call arrow, the arrow or the edges, oriented edges of the line graph is just you put an edges if UV is an edges with ST. If V is different of S, then it's 0. So the adjacency matrix of this big graph, there's a lot of 0.
So this LG body, every edge applied comes twice.
Yes, every edge has two orientations. Yes, so it's so the number of vertices is twice the number of edges. It's 2m, and then if I take the adjacency matrix, there is many 0. It's so the second bijection is exactly. In fact, it's the first bijection key, but written on the line graph. Imagine you are doing the same bijection. So you are following your path. The path is it's a world of edges, and then you are going to make a cycle. Is going to fall down, but the cycle is an oriented line graph, which means you can go several times on the same vertex, but never go twice on the same edges. As soon as you return to the same edges, the same orientation, then a big oriented cycle fall down. It's not a cycle, it's what we are going to call an oriented loop.
But, and then you have to come back to the original graph of the line graph.
So we have.
So you start with the path in the original graph.
So I do a path, and I'm going to give a bijection.
Then you make
from
the
this
path
path.
in the line graph.
So
Then you do the usual bijection.
yeah,
And
yes,
then you come back to the original.
yes. So I describe. I don't come back to the original description because the pieces of the heaps will be different. The self-evolving walk will be different. It will be a walk which never goes through the same edges twice, the same oriented edges. It can follow the same edges, but in two reverse directions. So let's make some definition. A trail, usually this is maybe the language of graph series. A trail is a path having all oriented edges distinct. This corresponds to self-evolving path in the first bijection. Self-evolving was all vertices were distinct. Now it's a sequence of edges, it's a trail, it's a path, such that all the oriented edges of the word or the path in the oriented linear graph are all distinct. And then I have the analog of cycle, the oriented loops. Oriented loops is equivalence class of trail, such that the trail go back to the origin from the, which means a trail is a path starting in U. It's a sequence of edges, then you go back to U. Your path go back to U, and the trail means that you never follow the same edges, same oriented edges twice. And oriented loop means you define this up to a circular permutation of the edges. So let's give an example. It makes it much clearer. So here you see it's a. So this is going to be the bijection. You see, you start from U. So you go first edges, you go here, you go here, you go here. So I am crossing myself, but it's still a trail. Then I go here, see I go here, I make a backtracking here. I go here, so until when I stop here, I get this. So this is called oriented loops. It's like a cycle, a big path, a cycle. We can go several times on same vertex, but it's never use the same oriented edges twice. And here, when I come here, I say A10, this edge is the same as this one. And then in the first bijection, so the bijection is going, then this is going to fall down, and this is going to remain. This will correspond to the self-avoiding walk, and this will correspond to the cycle in the first bijection. And this will be the bijection in the oriented line graph. You see, it's all these oriented loops will fall down. So this is, when I stop here, I have a trail. If I follow here, then it's no more a trail. I'm using twice the same oriented edges. But you see, I can use twice the same edges in two different orientations, and then it's still a trail.
So this is all in the original graph, right?
Mm-hmm. All the vertices are in the original graph. So oriented loops mean you start at one vertex U, you go back to the vertex U, all your word of edges are all distinct. I never go through the same oriented edges twice. And then I forget the starting point, or it's up to a circular permutation. So in fact, this is, if I follow these loops, it's a word in the edges, it's a word in the oriented line graph. The letters are edges, oriented edges, and these words are all edges, oriented edges are distinct, and it's up to a circular permutation. So this is what we call oriented loop. I think in physics they use this in different physics models. So I am going to define the new bijection psi, the same as key before, by replacing vertex by edges and replacing cycle but by oriented loops, and replacing self-avoiding walk by trail. A trail is a path which never goes through the same edges twice. So here is a description of the second bijection. So you have this path, a path omega become a word or a path, a sequence of edges. It's a word in this path in this oriented line graph. And then the second bijection is the following. So take a trail. Eta will be a trail going from U to V. I call a trail a path having all oriented edges distinct. And then I have the heap is going to be a heap of oriented loops. So oriented loop is equivalence graph of trail. Trail is a path going and starting to the same vertex up to a circular permutation. So this is a word in edges, E1, E2, En, where each edges EI is oriented edges. And then I describe the bijection. This is the analog of the first bijection. So you start with the self-avoiding, the trail in blue, which is above the heap is empty, the heaps is empty. And then suppose at a certain time t, you have a pair, you have a trail and a heaps of oriented loops. So you have your trail is this stop at certain vertex. And the trail, in fact, is going from a zero, always starting from a zero and is ending in ST, this blue path. And then suppose I have a heaps of oriented loops such that the projection of the maximal piece intersect eta. Same as the usual bijection. The concurrency relation between oriented loops is two oriented loops are concurrent if and only if they have a common oriented edges. So intersect means they have the same oriented edges. There is one oriented edges in eta, which is the same as in one of the maximal piece of the heap. And so I time t plus 1. So it's two cases. If the edges does not appear in the blue part, if you have a new oriented edges, then you add it to the blue path above. It's again give you a trail a path where no edges are repeated, and the heaps is invariant. Second case, if the new edges you are adding in fact an edges of this self-forwarding of this trail, then you cut your blue path, you cut it just as these edges, and a new cycle, in fact a new oriented loops is falling down, and you put it on the top of the new heap. See, it's the analog, exactly the analog of the bijection phi, except that you stop, cycle fall down when you follow the same edges twice. On the blue part, which is above, this loops is going to fall down, and then you continue. At the end, you have the blue part is a trail. It's never go twice in the same edges, and the heaps is the heaps of oriented loops. Such that the maximal oriented loops are touching, intersecting the blue path, which means they have a common oriented edge. And at the end, when you finish at time t equal n, then you have your blue path and your heap. So the analog of phi, when you translate everything, vertex become oriented edges, cycle become oriented loops. So it's the analog of the bijection phi, of the first bijection key, on the oriented line graph. So this is an example. You say you follow your blue path, and until the edges A9, you get a trail. You never go through twice the same oriented edges. But when you follow here, then A10 equal this one. So oriented loops fall down, and what remains is this trail here. So if you go on like this, you see, you can get a big, the heap will be really different. And then now proposition, if you have a path omega has no tail and no backtracking, if and only if the blue path theta has no backtracking and no tail, or in fact he has he can have a backtracking. Yes, you can go this, come back here, it's still a trail. If you go in a backtracking, you go 1, 2, 2, 3, and then you go back 3, 2. This is a backtracking, but the 3 edges are different. So a trail may have a backtracking, may have a tail. So the condition is there's no backtracking, no tail, and each oriented loops in the heap has no backtracking. So then I get a characterization of paths with no backtracking, but I need this much bigger adjacency matrix, much bigger graph, transforming the vertex into edges.
So is it possible to recover the old graph from the line graph and view this as a duality?
Duality is usually in planar graph, but here it's a... So the interest, I claim there was some connection with physics because of the Ising model. This is a paper Helmut in 2012. So in the Ising model, I should say Ising model, you have to count such what is called closed graph. So you have a rectangle, and closed graph means you have some green edges. Here is a grid, such that in each point there is 0 edges, or 2 edges, or 4 edges. So you have to count this kind of things according to the number of edges. But in fact, you have to count this with a big rectangle, go to what is called the thermodynamic limit. And then going to the thermodynamic limit, we will see that this is very convenient to take the inverse and to take heaps of such a thing. Heaps of such, so you have many loops here, to take heaps of such a things. And then, Helmut, what he has done, you can associate to this some oriented loops. You put some edges. So there will be many ways to put some edges here, but if you make a parameter with the number of times you turn left or turn right, then you can go back from this to the bijection with some paths. So it's very interesting. You can solve this by using this Heaps methodology, and you need non-backtracking paths because, of course, if you go back and forth in this picture, there is no green. There are no 2 green edges touching each other. So you need really associated to this some non-backtracking oriented loops. So this gives the second definition for the zeta function as a determinant, inverse of the determinant of this. Now everything is ready to give this second formula, where what is H8? So T is the oriented matrix of the oriented line graph. So T, you see, it's the adjacency matrix of the oriented line graph. So you have between edges Aj and Kl. So you put a 0 if j is different of k, and you put a 1 if j equal k. So this is the adjacency matrix of the oriented line graph. This is T. And now B is the submatrix, where you put a 1 or a 0 for a backtracking. The term ijji, it's a 2m by 2m matrix. You put a 1 if you are doing a backtracking. So subtracting from T, subtracting the matrix B, means you just keep the path in the oriented line graph, which are not making any backtracking. And so the formula is this formula. Now it's very easy to prove with all we have done, because the t times the logarithmic of this is a generating function by number of edges of pointed pyramids of non-backtracking oriented loops. Oh, this is also the sum of all circuits with no tail and no backtracking. Now you have to take we know from previous that is a generating function of pointed pyramids with no backtracking oriented loops. And you are pointed means that one of the edge of the maximal piece, which is a non-backtracking loops, is pointed. Which means if you start from this point, you make a circuit on the oriented line graph. So if you think just
Point is the starting edge.
yes, starting edge is a starting point. So taking by the usual theorem of previous chapter, I am taking pointed pyramids of non-backtracking oriented loops. And this is exactly starting from this. It's going to be the generating function of circuit with no backtracking and no tail. So I gave a proof of the equivalence between second condition and the first. You see, I have to go to this big matrix to characterize non-backtracking paths. But it's very interesting because we will use it. I will not explain the paper of Helmut, but in Ising model, but we will use this. Can be used in physics. This is interesting to have this bijection instead of the first bijection, to have the bijection in terms of oriented loops and all this story. So this is equal to this, which is equal to this. So we have the equivalence between 1 and 2. Now let's go to 3, the third definition of the zeta function, which is this one. So now I'm going back to the graph itself. Instead of taking adjacency matrix of the line graph, I am taking the graph itself, but I have a correction to do, and I have this extra term which is coming. So G, the graph, is M, the number of edges, N, number of vertices, A, adjacency matrix, incidence matrix of the graph, and D will be the diagonal matrix. D means that it's a diagonal matrix. The term dii is a degree of vi. So each vertex has a certain degree. And then I am going to take the t times the logarithmic derivative of this inverse of determinant. So here you have the Usually, if there was only this would be usual path. But then you have to have this term. So D minus I means that it's a diagonal matrix such that the term II is the degree of the vertex I minus 1. So this, I can write this. We know now that the logarithmic derivative of this is a Heaps of cycle, but with a certain weight. And the logarithmic derivative will be the pointed pyramid of such Heaps of cycle with a weight V. So what is the weight V? So let's take the vertices of the graph to be 1 to n. The weight V of ij equal t, as usual. But now the diagonal term, there is a correction. It's minus t2 multiplied by the degree of the vertex I minus 1. So see, I'm taking path. What means circuit or path like this? I am taking circuit, I am taking path, so that it's a regular path with the adjacency matrix A, but sometimes I am allowing some loops. I should say at the beginning that the graph G has no loops, but now in my path, I am allowing some loops, and the loops is weighted by minus t2 multiplied by a number which is the degree of the vertex minus 1.
So you start with a graph with no loops.
Yeah, a graph with no loops. I am taking path on this graph with no loops. I am taking circuit. I go from you, I come back to you with no loops. And sometimes I am allowing some loops. I am adding some loops because I have new loops here. And this loops is weighted minus t2. It's count by double for, and it's count for there is a number, a multiplicity of the loops, which is the degree of the vertex minus 1. So immediately come to your mind, if you love involution, which is going to be killing involution, that if you have a backtracking here, look, I go here, I make a backtracking, which counts for T2. Why not to kill the backtracking and replace it by a loop, which will be minus T2? But the backtracking you are doing, the number of ways of doing the backtracking around this vertex is precisely di, the degree minus 1. Because these edges, if I was doing this, using these edges as backtracking, then it will be no more backtracking here, it will be a backtracking here. So, there is as many backtracking on this vertex. So you see you're killing involution. I am going to associate to all the dii minus 1 backtracking, I am going to associate to loops, which will be weighted minus t2, the degree minus 1. Very good.
What if the green thing is already going in and out?
The green things, this one?
Yeah, that itself is a backtracking.
Yes, no, look, the path is doing this. Okay, and now I can make a backtracking like this, check. There is a number of backtracking I can do when I stop here. Number of backtracking can be, it's exactly the degree minus 1. And then you follow your path. You just follow like this. Only thing you are not allowed to use as backtracking is these edges. But I suppose I am not on the first point of the path. So my involution will work. We will see what happens with the first point. But if I am already on beyond the first point origin of the path, even if I make, suppose I have an origin U, even if you make many loops, I have a lot of loops. But as soon as you make an edges, where you go outside of the first point, then there is an edges in green. And if you have backtracking, I can cancel it with all these loops weighted by this. And so the idea is, if I have a circuit with possible loops, then you follow, except the first point, you follow after the first point, and you take the first time there exists a backtracking, or the first time there exists a loop, which is weighted by the degree minus 1. And then you exchange the two. So you are killing everybody. You see, you are killing a loop weighted by this, you are killing with all the possible backtracking you can do on this step. But there is a problem. Yes?
But why are you saying that the green, after you do the backtracking, you
Yes.
cannot go back by the same edge as you came in?
Yes,
come
I
in
have-
with the green, then you go backtrack, and then you go out again.
If you do backtracking like this, and then
again,
I go out, yes?
no, go out from the same way.
Yes, like this?
No, like that.
Here?
Yeah, why not?
Then you are doing a backtracking here,
Yeah.
which
So
is
then-
going, then it will be reduced to loop here. This backtracking, tac, tac, is referred to this vertex.
No, but then after you do this involution, then that is not the first backtracking anymore. So you said you take the first backtracking.
Yes,
or the first
yes.
loop. Oh, but then that's already not the first.
But if you have, if you are doing,
Oh, the loop. Okay. The loop comes before the back.
yes, you take else, when you follow after the first point, else you look a vertex where there exists a loop, or else a vertex where you are going to do a backtracking. I change the two and I kill everybody with the multiplicity of the loop. The problem is at the first point, because. So I'm killing everybody after the first point, but for the first point, if you are starting at the first point immediately with the backtracking, so you replace by your loops, but the loops, is the number of possible loops, is a degree minus 1. So you can kill all the backtracking except one of the edges. Number of edges at the first point is a degree. So I will call a special edge where I cannot do a correspondent with a weighted loop. So if you have a weighted loop, then you can associate all these possible backtracking at the origin, except this one where there is no way to kill it. But we are taking the logarithm, which is pointed pyramid of cycle. And in the case there is a loops at the origin. This is the maximal piece. And the maximal piece of the pyramid has a weight T2. And if you remember the paradox, which is not a paradox of the logarithmic, in fact, the loop which is weighted by T2 is counted twice. When I count my loops, I have to consider the loops as I have the possibility to point it twice because the variable is T2. So the maximal piece, if there is a loop as maximal piece of the pyramid, in fact there is two possible loops. There is a blue and a red one. So in fact it's more complicated. I have two possible loops which are weighted by the degree minus 1. But this is very good because I did not consider the tail. And when there is a tail, the tail comes from the origin. And the tail, I can cancel the tail with the blue loop. The red loop is going to cancel the backtracking at the origin, and the blue loop is going to cancel the tail, which I can get as soon as I start the path. And now if I have a tail going from U to V, the number of possible tail is exactly the degree minus 1. Because these special edges, see when you have a tail here, you are going to delete, starting in U, but the tail is going to be killed with these loops here of degree minus 1. And the number of possible tail is a degree minus 1 here. Maybe I'm a little confused. But this is the idea, you see. The idea is to kill everybody, except at the origin there is some special thing happening. There is two colors in the loops. There is two possibility to cancel the tail or to cancel the backtracking. And I am in trouble because what remains in this involution, it's circuit with no loop, no backtracking, except maybe at the origin. Maybe at the origin there is some special backtracking on the special edges where you cannot kill the edges. And so I have it's not a proof, but it's an idea which gives you that this logarithm of this big thing is the sum of the logarithm of this, which gives you this, plus the logarithm of this, which gives you this circuit with a special condition where I am Pacific man, so I don't kill everybody. I need some more powerful tool to kill everybody. What you have to do, you see, it's if you want to prove the equality, to prove that you have to do that this special circuit where there is this condition star, it's going to be the circuit I want here with a term which is going to cancel with this one. And this, I thought I would have a proof before coming here, but I am stuck, and I leave this as a research exercise. Helps to complete the proof, to simplify. But you see, the idea is so simple. Backtracking, you cancel, you get exactly degree minus 1. At the origin, taking the pyramid, I have two colors for the loops if it's at the top. One of the loops cancel the backtracking of the origin. Other loops cancel the tail, and something is not cancelled, and I don't know what to do. So I need your help. Maybe I am stuck, or maybe it would be nice to give a proof like this. It's to have similar proof, all the t times the logarithmic of the, to have a direct proof with the heaps of pieces.
This comes from physics, this last one.
This oriented loops is related to physics, yes. But and so we were starting from the Riemann zeta function and to try to extend it to some prime of the graph, and we take equivalence class of prime with no backtracking. But why to bother with no backtracking? We have seen that the idea, my third identity, I am really embarrassed. And when you do no backtracking, you need to go to a huge matrix, Hutton matrix. So let's delete this condition. Take equivalence class for all prime circuit. Why not? And this has been done because there is Bartoli, there is a paper by Bartoli. We define the zeta function with a parameter taking care of the backtracking. And if you put the parameter equal 1, then you don't care about backtracking. If you put 0, you get no backtracking. So you get the two zeta function, an interpolation between zeta function with no backtracking, no tail, and zeta function with where you don't care about no backtracking and no tail. So if you do this definition, which is simpler, why not? Then the zeta function, you see this. So this becomes, instead of heaps of balls, you have heap of cycle. This becomes the equivalence class of prime circuit. And this becomes the inverse of determinant. And this is what is doing, this Giscard and Rocher, these people are doing to extend number theory to parse in graph and all the function in number theory to try to extend them in graph, but using heaps of cycle. Not using, don't bother about no backtracking, nothing. This was maybe valid in the context where Iara introduced his zeta function. It was with some group, with some regular graph, etc. And then it was valid also for the condition with physics. But why not to take off this condition, forget the condition, and then work only with heaps of cycle? So they call this the commutation class of heaps of cycles. They call this a hike. Hike, it's like a randonnée. And so there is a lot of work to do, you see, to try to extend all number theory to this kind of things, and then maybe to go back to number theory, to do the L function, Artin function, etc. So there is a book by Terrace and Stark about Riemann zeta function and L function. And in fact, in this book, to prove that the equality between 1 and 2 and 3, they make a lot of some computation, and then they go back to the Jacobi theorem, that the exponential of the trace of the log equal exponential of a... So they go back to this theorem after some manipulation, but we know that this theorem comes from pyramids, taking logarithm, take pyramid. Here also we take logarithm taking pyramid. So in fact, this basic lemma, that t times the logarithmic derivative of heaps of cycle is exactly the pyramid, pointed pyramid, this basic lemma give you at the same time the Jacobi identity, give you the zeta function, give you several other things. So instead of trying to make calculus to go back to this linear algebra, why not to go straight to the lemma, which is the source of all of Jacobi identity of all different identities. So this is kind of a source lemma. So it's good to try to come back to the source. Always you have to come back to the source in every subject. Yes,
But
Amri?
I still don't understand. So
Yes.
the moment you have an infinite graph,
Hmm?
you need to put in some. You need to talk about convergence,
Yes,
and
yes,
so you need to put in weights for t.
yes. So here we have only finite graph.
Rational functions. Yeah.
You have finite graph except for the for the Riemann zeta function, where the graph is infinite. But
If you take the Z2 lattice, is there
Mhm.
some nice weights for which you get some nice Dirichlet function?
I don't know. Maybe this is a subject. It should be, yes. Here I restrict to finite graph.
But it's
This is
studied
another
or
story.
probably.
Yes, probably. It's another story. Okay, we'll finish a few minutes with spanning tree, and we'll finish this chapter. A few more slides, and we'll have finished. So 10 minutes about spanning tree. So we have seen we cannot close this chapter without giving the formula for the number of spanning tree. So spanning tree we have seen is this. A tree which is underlying the graph and which covers the whole vertices of the graph. Then for a spanning tree, for a graph, you have the Laplacian matrix. It's called Laplacian matrix. Is L equal D minus A. So D is a diagonal matrix. Dii. Now Dii is exactly the degree of a one slide is missing. So Dii is the degree of the vertex. And A is the adjacency matrix. So it's a minus A. So you put a minus 1. It's a graph without loop. You put a minus 1 each time there is an edge between I and J. And for the term diagonal, you put the degree of the vertex. Example. So here is an example. You see this is this graph. 1, 2, 3, 4. In diagonal, I put the degree of 1, degree of 2, degree of 3, degree of 4. And minus 1 everywhere there is an edge. Between here there is a 0. But everywhere there is an edge. So you have a certain matrix. And here I took the determinant of the minor principal minor when I take off the first row, first column. Cancel the first row, first column. So you get this 3 by 3 determinant. And this 3 by 3 determinant is 8. And the theorem tells you, the famous matrix tree theorem, tells you that the number of such spanning tree is exactly this 3 by 3 determinant, the principal minor. In fact, if you take any minor of this matrix, up to the sign, it will be always the same number, the number of spanning tree. If you take on the diagonal, it will be positive, but any minor will give you the number of spanning tree. So it is the theorem. The number of spanning tree of the graph G is a minor II of this Laplacian matrix. And I give you a proof with a nice involution. Now involution is nice, it's gentle. We are going to eliminate the term 2 by 2 is a nice way. No problem with as before. So just recall the definition of determinant. Determinant is minus 1, the sum of all permutation. Instead of writing in the usual, I write it as a cycle decomposition of the permutation. So this is the V, the weight of the cycle as usual is the product of the weight of the incident matrix. Number of inversion of the permutation is the sum of the inversion of the cycle. And the inversion of the cycle is minus 1 power the length of the cycle minus 1. And now the cycle are 2 by 2 division, but it covers the whole graph. Before, when there was the matrix 1 minus A, it was a triviality of cycles. They were not covering the whole graph. Now they cover the whole graph. all these cycles. So here is a picture of the. So taking the minor, the one by one minor, I take off this point 1, I put it apart, and then I put some 2 by 2 disjoint cycle. So in blue, this is a cycle coming from the incident matrix. Each edge is weighted -1. In red, this is the loops coming from the diagonal term, which is a degree of the. Each loop represents the degree of the vertex. So in fact, the correct picture is this. See, for each vertex, each loops in red, you put an edges corresponding to a choice of one of the edge connecting this vertex to another vertex. Maybe it can connect to one, can connect to a blue, etc. So a loop is weighted by the degree of the vertex, which means I am choosing red edges starting from this vertex and going everywhere you want. So in the picture, you have some blue cycle, you have some red cycle, and maybe you have some edges going to the red cycle. So this is the picture, and then there is a very nice involution, very simple. In a certain way, I can exchange a blue and a red cycle. But what is the weight? The weight of the blue cycle was the number inversion of the cycle, which was -1 power the length -1. And the red cycle, is it this?
You have -1 for each edge.
Yes, you have -1. No, you have -1 for each edge. No, this is not true. You have -1 for each edge of the blue cycle.
No, for the red.
For the red, yes. No, the red comes from the. Yes, because it's a. So I am confused now. The -1 coming from the inversion, the blue cycle comes from the inversion, so it's -1, the length -1, but each edges in blue is weighted -1 in the matrix. So you get, in fact, you get a -1, in fact. You get -1 power the length of the blue cycle, multiplied by -1 the length of -1. So the total is a -1 for each blue cycle, and here each red cycle is plus, because it's a loop. In a loop, it was the degree, the diagonal term was positive, and in the loop, there is no inversion. So in fact, each red cycle is +1, each blue cycle is -1. There is a mistake there. So the involution is going to kill a blue cycle with a red cycle. And so at the end, if I can kill all the blue cycle, what remains is only the red edges. So there is no red cycle, no blue cycle, no cycle at all, only red edges, and these red edges, what remain, will give you a trees which rooted in one. And that's the proof of the theorem. See, it's very simple. This involution. As soon as you translate everything, the Laplacian matrix in terms of the picture, then you see there is two kinds of cycle. If you change the color, the sign is changing. So you can have an involution in a certain way. You will take the minimum cycle, etc., and you will define the involution easily. And at the end, there is no more cycle blue, no more cycle red. What remains now is a trees, which is rooted. All the red edges, there is no cycle, are sure to go to one, the root of the spanning tree. And you can extend this to, this is a cofactor, any cofactor Ji, then there will be, this is an extension of the proof, and you can get the same things, the same involution, will give you the number of spanning tree rooted in J, and there may be a plus or maybe a -1, depending on the cofactor of the sign when you delete G and I. And I will finish. So if you have any path, you see any path give you, in any graph, any path give you this pair eta E. The pair eta E give you, if you look above the path, if you look all the maximal edges, you get a spanning tree of the spanning tree for the vertices covered by the path. In fact, it's not totally true, because if I take this path, you see, I go here, I go here, I go here, and come back here, I go back to V, then I make a cycle. It's possible in a self-avoiding walk to make a cycle, but because I am just taking the maximal edges. Of course, if you are putting a point here at the end, then the cycle will fall down, and it's still a self-avoiding walk. But if you look above a path, I mean, you are taking all the maximal edges for the flow related to the path, then this may happen. If you have a cycle above the path, then necessarily the ending point must belong to the cycle. Because if it was not belonging to the cycle, then you have to go to the ending point, so you should go outside the cycle, which means that this point, one of the vertices should be covered twice. One of these edges would not be a maximal edges if you are going outside of the cycle to go to V. So V belongs to the cycle. And in fact, if you delete these edges, then you get a tree. And if omega stops the first time it arrives in V, then you get a spanning tree where the maximal edges and the heaps, you get a heaps of cycle not containing V. And this was, you have no time to explain you, but this was to go back to the Wilson algorithm from a random spanning tree. You remember in the previous chapter, there was a proof by Marshall in the paper Temoleman. So I remember you choose the point x1. You have a total order on the vertices of the graph. You choose a point x1, then you go by random loop erasing walk. As soon as you touch x1, you stop, and then you start another point. You have a loop erasing walk, etc. So you go like this, and what you get at the end is a spanning tree. And then the Wilson proposition is that the John law of the spanning of T and the occupation measure at the stopping time of the algorithm does not depend on the order chosen on V minus x1. And there is a proof of this, that it does not, the distribution law does not depend on which order you put the point choosing when you choose each of the paths in the Wilson algorithm. There is a proof by Marshall working with heaps of PCs. So when you do the algorithm, take all the heaps of all the erased loop, keep the heap. So, but each time you are doing the first, when you do the first, you do the first pass, then you have a heaps of cycle. Then you do a second pass with taking the minimum of the point in the total order. You have a second pass. So the heaps put the cycle on the top of the heaps of cycle. So each time you have a new pass, put all the heaps of cycle one over another. At the end, what you get a spanning tree, and a whole heaps of cycle coming from all the paths you have done in the algorithm. And it's easy to see that this heaps of cycle, in fact, it's a coding of what you have done in the Wilson algorithm. You can completely reconstruct all what you have done. What will you do? You take this is starting point, this is a spanning tree, take the minimum point, which is in spanning tree, x2, so you have a certain path. So take this path and push it as we do as usual. So you are going to embark a whole heaps of cycle below this first blue path. What remains will be a heaps of cycle which does not intersect eta 1. In this big heaps of cycle, then you take in the spanning tree, take the minimum point in the spanning tree, then push the second self-avoiding one, etc. So you push the blue path one by one. You reconstruct in each all the sequence of points you have done. You have taking the heaps of cycle is decomposed into a product of heaps of cycle. Sorry to go very fast. And all this probability you have to work with, it's exactly, in fact, the product of this weight. And this weight depends only on the T and the E. It does not depend on the way you have chosen the point. And so this gives a proof that this algorithm is not dependent of the choice of the different point. And it's only because of it's encoded by a spanning tree and a heaps of cycle. Sorry to go very fast, but I want to finish this chapter 5 and next lecture, next next lecture will be, next chapter, fully commutative element in Coxeter group. So I will do only one Coxeter group, the symmetry group. There is many papers on all the other Coxeter group, but I cannot do everything in there. So we'll have an idea of all this other chapter about. Okay, so thank you very much.